Thank you, Matt, for the introduction and for the kind words, and thank you also to Bill Mars, Jim McIntyre, Jim Cutnow, and the rest of the Tire Society Executive Committee for allowing me the opportunity to come here and share my story with you today. It's my honor to share with you my journey covering past 30 plus years in the tire vehicle industry and to talk to you about the advancement of the virtual world in motorsports as I lived it. Please know that this is not meant to be an exact historical record on the application and advancement of engineering in motorsports. Rather, I want to share with you today my experiences, what I witnessed, and what I participated in during my career. Before I start, I wanted to take a quick minute to acknowledge the great group of friends, employees, and family who've been by my side throughout my career, who have shared in all the experiences of both OEM and motorsports engineering development, and who have challenged me and who have been there through all of our successes and some failures. Thank you for your guidance, your friendship, and all the help you gave putting this presentation together. I believe most of you know me as the president and owner of Stackpole Engineering in North Canton, Ohio. My wife Tracy and I started this company back in 1999 in the basement of our home. While the company has grown over the years, we take great pride in our ability to maintain a family-run small business atmosphere, and we have proudly served the tire and vehicle industry for the past 20 plus years. Most of you also know me as one of the tire testing and tire modeling old guard, one of those people who have been in the business of tire testing and tire modeling for a whole lot longer than we really care to acknowledge publicly. On the surface, it's a fair representation of who I am and what we do at Stackpole Engineering. However, it's only a part of my background and really only a part of what we do here at SES. I hope that this presentation will give you a better understanding of our involvement in the tire vehicle industry and what role we played in the development and advancement of the virtual world. So, our agenda for this talk is, first of all, an introduction of me, my background, and some of the areas I've worked in both engineering and the virtual world. Definition on how the virtual world has changed over the years. Virtual world in motorsports, a little bit about my beginning there, specifically in motorsports. A little bit of a case study that we wanted to give to you today regarding the growth of engineering in NASCAR, how we went from no engineering in place to where we are today with the pretty firm use of the virtual world. The importance of virtual world in motorsports. Why is it so important to engineering? Why does it mean so much to the engineers in motorsports? The advent of the simulator and the virtual world in motorsports. Again, the newest technology, and how are we applying it? Why is it important? And then finally, the future of the virtual world in motorsports, and then some closing remarks and some credits. So over the course of my career, I've had the fortune to develop and deploy various forms of engineering tools, simulation methods, and virtual environments, and have witnessed tremendous change over those years. Seems like whatever position I held, my focus was always on the use of computers and the virtual world to solve real-world tire vehicle system problems and to advance the role of the engineering process. Whether it was in supporting tire designers in my early years, creative custom tire vehicle simulation software, or developing tools and methods in support of either OEM or motorsports programs, I was fortunate to witness and participate in the growth of the role of engineering and the virtual world. While all these programs have been exciting and challenging, there's been none more fulfilling to me than all of the work in motorsports. I had the pleasure of working with an extremely talented group of engineers that were focused on making significant contributions to the success of their race teams, as well as the art of engineering in this extremely stressful and fast-paced environment. At its core, this motorsports engineering problem is the quintessential engineering problem. So it might surprise you to hear me say that after all those years of motorsports, after all those years of enjoying what I was doing, there were times where I felt like engineer was a swear word. And let me explain what I mean. So I've heard this phrase or a variation of it since I was young. Growing up in New Jersey, my father owned an electrical contracting company, aptly named Stackpole Electrical Services, or SES. My dad made sure I was always busy. Any spare time that I had, I was working with him in the trade. I can't tell you how many times I heard the phrase, these darn, not always the word he used, engineer. Whether it was us trying to rewire a machine or lamenting over a machine we were trying to understand, or underneath the car trying to work on an automotive project. My dad had a really strong love-hate relationship with engineers. Much to his dismay, but also with his support, I ultimately became an engineer. I graduated from Stevens Institute of Technology in Hoboken, New Jersey, back in 1985 with a Bachelor of Mechanical Engineering degree. Earlier in my career, I was fortunate to be part of an engineering-focused team in the nuclear equipment design industry. Every decision that we made was typically driven by analysis, simulation, and engineering design results. Results were checked, and in our case, often checked multiple times, and oftentimes compared to results from an independent contractor to ensure that our answers were accurate and met all the specifications required. After a short 5-year stint in the nuclear equipment design analysis field, I had an opportunity to move to Bridgestone Firestone. There I worked in the advanced engineering group from 1989 to 1991, reporting to Dr. Marv Jansen and Dr. Joe Walter. It was the role of the advanced engineering group to develop and apply advanced technologies to the tire design process, and to develop and apply tools that would support the tire submission process to the OEMs. Because of my background in FEA analysis, I was tasked with developing processes and building FEA models for handling performance analysis. Since this was early on in the FEA modeling process, I have to admit the impact was pretty small, but it really served as a good research tool on our learning of how to apply FEA processes to the tire design process. I also was fortunate enough to work alongside a really talented group of engineers who were developing tools and methods around the tire vehicle simulation field, and they were using Adams at the time. And keep in mind, this was early Adams, before Adams before Adams car. It was Adams at its core, and most things were done through a very manual process. Most of this effort was focused on developing models and simulation events that would support design decisions for the tire designers. At the time though, OEMs were also starting to ask for simulation support as part of the tire design process or submission process. So this was really my first experience with the development and validation of tire and vehicle models to support tire development. I completed my master's degree in 1991 from the University of Akron with a focus on finite element analysis. And that degree opened up an opportunity for me at the Goodyear Tire and Rubber Company, where I began working for Dr. Dave Glemming in TVET, or Tire Vehicle Engineering Technology, in the handling department. It was there I helped to develop tire models and vehicle simulation methods to support the OEM tire submission process. Pretty typical for the time, vehicle manufacturers were requiring that tire manufacturers supply them with both tire models as part of the submission process and simulation support to ensure that those tires being developed would meet the predetermined specifications for things like handling, stability, noise, and ride. After several years in TVET handling department, I was asked to join a newly formed engineering group in race tire development called Advanced Engineering. It was really the role of that group to try and take some of the processes that we developed on the OEM side and apply them to race tire development and the tire development process. You know, we all felt how hard could it be. We'd been successful with it in the OEM world. It should be pretty easy to apply that same technology in the racing world. Unfortunately, or fortunately, I was soon to find out that we have many years of challenges, new experiences, extremely difficult problems to solve, and multiple successes and some failures along the way to be experienced. This is where I'd like to start my story. Before we get started, I want to take a minute to define what I see as the virtual world. The term virtual world, as many of us experience it today, has changed significantly over the course of my career, mainly due to fundamental changes in available technology, but in some strange way also due to the availability of capital, because as we all know, technology costs money. All of us are familiar with the current definition of the virtual world, sometimes called virtual space. Namely a computer simulated environment where engineers can investigate designs and perform analysis without the need for any physical prototypes or any physical testing. Early in my career in motorsports, we thought of the virtual world as merely Excel spreadsheets that we used to analyze tire and vehicle performance and physical test data with the sole purpose of seeking to understand the performance of both. While these were crude compared to today's standards, they were invaluable back then because they gave engineers access to information and analysis methods they didn't have prior to that. These tools included MATLAB and Excel-based tire data analysis and plotting programs, simple kinematics processes, basic steady-state vehicle dynamics calculations. At the time, these tools and methods gave engineers access to information not available before and gave them the ability to start formulating a base understanding of tire and vehicle performance. It's also allowed them to start investigating a lot of the what-ifs that engineers are known to ask. As time progressed, in typical engineering fashion, we started asking more questions, demanding more detailed data, started developing more detailed processes and created more advanced models and tried to deploy more useful tools. The status quo was never good enough, especially in racing. Because of this drive, focus shifted from simple analysis methods and lab testing to advanced analysis and engineering tools, advanced lab tests, dynamic simulation methods, and eventually to the virtual environment we're all familiar with today, namely the driver-in-the-loop simulator. I will be discussing most of these forms of the virtual world as part of this talk today. So with this definition, a variable definition of the virtual world in mind, I want to take some time to circle back to my time in the advanced engineering group at Goodyear Racing in the mid-1990s. During that time, Goodyear was heavily involved in Formula One, and I was tasked with developing the tire models and the simulation methods necessary to support not only the team requests for information, but also the race tire design process. And while engineers and the engineering methods were a norm within the Formula One ranks, they had built up large organizations that seemingly had limitless budgets. That level of detail and that level of capability and resources were not yet available in the tire manufacturing world. So while race teams pushed us for all of this information relevant to the tires, we were only in the early stages of developing the testing methods and the simulation methods required to support not only their requests, but also the tire designer's requests and the tire design process. As I noted, my initial charter was to take a lot of the OEM tools we had developed and port them over into the race tire development process, and to try and come up with engineering metrics that would help our race tire designers and their process, as well as help us all understand the interaction of the vehicle on tire performance. We wanted to find ways not only to understand the operating conditions that the tires saw, but also find ways to try and incorporate or understand the driver comments and driver feedback and try and equate them back to some calculable vehicle dynamics metric. And also, obviously, the methods were going to be used to help support the team requests. We began by focusing our efforts on developing performance-based tire testing methods for race tires, developing custom-specific tire models, and custom simulation processes. As I noted earlier, at the time there really was not a lot of internal programs available or models available to us to evaluate or estimate or simulate the tire vehicle system in racing. We needed to learn what was required to best support the tire designers and the questions the teams were asking us. but also what technology was available at the time that would be able to be applied to solve the problems we were trying to solve. And equally as important, what information we could ascertain from the teams. Getting vehicle information from the teams was critical to us as we started to develop our vehicle models in support of the simulation. We started with basic steady state analysis of the car in the corner, focusing all of our efforts on single runs at predetermined locations around the racetrack, and analyzed each one of those locations versus some baseline. This provided us with, at that time, the first real look at estimated loading conditions for the tire in service. For all those folks that are computer aficionados, this was done early on an SGI Octane. At the time was about $30,000 worth of equipment. A lot of money for a desktop computer. And at that point required a lot of upper management sign-off before we could get it in-house. We also used Adams, and this is early Adams, well before Adams Pre and Adams Car, where all the work was done pretty much manually. On occasion, we took that Octane and went to the racetrack and supported tire testing, where we would sit in the hauler and the crew would come in, we'd analyze a setup, they'd go out and run that setup on the racetrack, collect that data, we'd come back and correlate against what the simulation said. We would look at changes to the race car, model them again, and they'd go back out and make another run. And we continued to do this for a number of years, trying to get a good correlated model. With all this simulation effort going on, we also had effort going on the development of new tire testing methods and the development of new tire models. We started with basic square matrix tire testing, and we ran the normal velocity rams, pure cornering, pure dry brake, combined testing. And initially all that data that came out of that testing was put into Excel spreadsheets. And those Excel spreadsheets allowed us to display the force and moment curves, allow us to evaluate the effects of inflation pressure, the effects of inclination angle, load dependencies, and all the things you might want to know about the tire. And at the time, that was the first look a lot of these teams had at tire data, so that information was extremely useful. Over time, we then started to use that information to develop basic tire models to help support simulation efforts. We started with basic 96 Pacheco models and used that model for a number of years. We then progressed from running single steady state point analysis simulations to full lap dynamic simulations and implemented custom race tire specific tire models. And all of this gave us a much clearer look at what the race car was doing on a full lap around the racetrack. That was great for looking at individual one setup at a time analysis, but as engineers always do, we decided that wasn't sufficient enough. We then started looking at design of experiment methodologies and AI methodologies to allow us to start looking at an infinite number of combinations of setups and effects of tire design and tire changes on the overall performance of the race car. While all this could be considered crude now for all the things that we're doing now, at the time this was a huge step forward in terms of supporting not only the tire design process, but also the teams in their quest for trying to optimize their race cars. After several years of supporting Formula One, I moved to the world of IndyCar to support both the teams and the tire design process, utilizing these same newly developed tools and methods. I found that while IndyCar trailed in their implementation of the engineering process and the availability of tools, they were on the exact same trajectory as the Formula One teams were on years in advance. And they were ultimately trying to get to a very detailed engineering process and a more refined use of the virtual world to support all of their internal chassis design work, their setup optimization work, and their race day adjustments. So with all my experiences in other forms of racing and with the exit of Goodyear Racing from both Formula One and IndyCar series, and with all the progress that we had made in the area of tire modeling and simulation development, we set our focuses on NASCAR to implement the same exact engineering tools tire modeling and simulation methodologies we had deployed in the other forms of racing. And once again, our initial goal was to better understand the environment our tires were operating in and to give our tire designers better information to support their development process, as well as supporting the durability analysis and testing that's critical in racing. It became pretty evident after asking questions of both the teams involved in NASCAR and some of the manufacturers that the data we were collecting, the processes we were developing, and the methods that we had might be very useful to them in their internal design process. Based on my experiences in other forms of racing, I was expecting a smooth transition into working on in-depth projects with the teams and obtaining very detailed information from the teams to support our internal vehicle simulation and tire design processes. I quickly learned, unfortunately, early on that engineer truly was a swear word in NASCAR at that time. And let me expand upon that and provide some background. Before we get going any further, I just want to emphasize that this is in no way, shape, or form a critique of NASCAR or anybody involved in the sport. It merely is just being used as an example. And note that all forms of motorsports have been through this exact same evolution over time. Some just got started a little earlier. As I stated before, I started my career in NASCAR in the mid-1990s, and I put together this engineering and virtual world time continuum for NASCAR to illustrate the typical growth path from a world of no engineering to a world of full use of engineering, simulation technology, and the virtual world. So the first block of time I want to talk about is the early 1980s through about 1990. During this period of time, there was no engineering at all as part of the process, and there was no tools available, whether they be physical tools or virtual tools, to support chassis development or race weekend preparation and setup optimization. Most decisions were done by an extremely talented, experience-based crew chief who had amassed a collection of notebooks of data and real-world test and race information about the car. And these books and data were not only used to prep the car for the race weekend, but also adjust the car during the race weekend. These crew chiefs essentially had 100% control over how the car was built, assembled, and raced. And at this point in NASCAR timeline, a great number of suspension parts being utilized were still production OEM parts, and they were quote unquote being adapted for use in racing. But please know these guys were really good at what they did. They knew their car, they knew how to adjust their car, they knew how to interpret driver comments, they could take visual cues from the car as it was on the racetrack, they would look at lap times and make adjustments just based on their experience and these data books they had available to them. They also knew how to make full use of the rules at the time. At this time, rules were less extensive and there was a lot more latitude to design and optimize your car within those rules. Most of the focus for teams in this era was to find advantages in the area of durability, whether that be suspension parts, engines, or tires. These guys were searching for tenths of a second, maybe a quarter of a second or a half a second, and they felt that those were achievable gains. But the biggest advantage you had over your competitor was to survive the race with no parts failures. And this process continued on until about the mid-1990s. So that takes us now to the 1990s, kind of the mid-1990s. This is really where engineers started showing up in the sport. Any engineer working in NASCAR at this time would have typically been brought in as a resource from one of the OEMs that was participating in the sport, and or by one of the teams that might have had affiliation with another racing series, such as the IndyCar series. Either way, the engineers were being brought in to try and help the teams work with some of the engineering tools that were available to them at the time, whether that was wind tunnels or KNC rigs or inertia rigs, and also to help them implement some of the tools that they had already been using in the other racing series. During this time, engineers could have been thought about as a necessary evil for the NASCAR teams, and often put in some pretty adversarial roles with the key decision makers, which at that time was the crew chiefs. This is probably the time where engineer as a swear word played out pretty heavily. As was told me by some pioneers in the sport, engineers were essentially being used at this time to focus on looking at the existing data that they had collected and to try and make better decisions from it. They were hired to collect and process all the physical test data, potentially to implement some instrumentation systems, and really to continue to build the massive data books that teams had and that they were accustomed to using. They were not initially brought in to develop any virtual world, any simulation, or anything that would be designed to support both their in-house design process or their optimization when they were at the racetrack. So during this time, the easiest inroad for technology and perhaps the easiest inroad for the engineers in NASCAR was the application and the understanding of aerodynamics information through the use of wind tunnels. This tool offered a bit of an instant gratification for the traditional decision makers, where application of not only the concept designs as well as the importance of QA process were easily measured, and they were quantifiable and able to be validated at the racetrack. At this point in time, there was very little known about tires other than the experience-based knowledge teams had amassed through the years. One of the first impacts we seem to have on the sport is when we started to provide some pretty basic tire information to the teams via just Excel spreadsheets with general plot creation capabilities. And this in turn, by providing that to the teams, we were able to leverage some vehicle information back from them as we started to develop our internal process. NASCAR is a place where the great equalizer is the fact that everyone has to run the exact same 4 tires. The teams that were making the best use of the information about those tires to help improve speed and degradation of the tire through a race were typically those who were successful. So having some knowledge at whatever level was seen as a large advantage. In terms of tire information, teams really only wanted to know about optimum pressure, and every once in a while wanted to know about the optimum toe and camber settings or the preferred alignment for the tires in service. Now that tire data was starting to become more readily available, teams started to focus their efforts on the operating environment of the car and the tires on the racetrack and tried to make better use of the tire data that was being provided to them. At this time, tire models were being developed to help support this tire data analysis methods, really not being developed for any kind of simulation analysis. Engineers merely wanted to know what the best hot and cold pressure was, what the best inclination angle was, and what kind of toe they need to run in order to make best use of the tires and to develop the optimal performance of those tires during the race. Note that the more data that we provided, the more questions they asked, the more detailed information they wanted, and this would go on, and this was really the prime motivator for me to start Stackpole Engineering Services, to support this growing interest in tires, tire modeling, and tire data. So now we're in the era of the 2000 to 2007 timeframe, and I've titled this the era of the hardware solution. This was the beginning of more comprehensive lab-based tests, such as pull-down rigs, 4 and 7 post and now 8 post rigs, and the expansion of the infrastructure required to support this lab-based testing. These rigs were being installed at either team facilities or at OEM centers in support of a better understanding of the race car and the ability to evaluate prototype parts and vehicle setups. As is typical in my experience, engineers developed some pretty specific techniques to extract the most out of this data from the testing. This also allowed engineers to investigate designs, setup changes on the race car without ever having to go to the racetrack. While being very effective method to understand their race cars, the process typically required physical cars, physical parts needed to be manufactured, and very lengthy test sessions. In fact, a lot of times these lasted for days and sometimes with varying results. While this testing allowed engineers to evaluate changes, they didn't always equate to improvements on the racetrack and didn't always equate to changes that the driver would even notice. Regardless, teams and manufacturers continued to press forward, gaining experience with the testing methodologies and working towards making these methods be part of their mainstream design and optimization process. At this point, engineers and the crew chiefs within NASCAR started to develop a better understanding amongst themselves, as well as the why and the how behind how these cars worked. But this is just now another collection of information within this silo of technical data. So now they're going to the racetrack with briefcases that not only contain the historical data they previously had amassed over the years, but now technical information such as wind tunnel data, gear ratio charts, engine dynamometer data, vehicle performance data, kinematics curves, shock dynamometer data, and the list goes on. And all this data had to now be stitched together basically with experience and intuition. These silos of data, I feel, now represent the start of what would be considered the virtual world in NASCAR. And know that teams at this point in time were looking for gains or speed improvements of somewhere in the order of 1/10 of a second. So we've now gone from 1/4 to 1/2 of a second gains in previous eras. We're now fine-tuning that down to about 1/10 of a second. Now we're in a year of 2001 to 2010 timeframe, and aptly titled the era of the offline software solution. So in parallel with the buildup of all these advanced lab-based testing methodologies, simulation development efforts really began to get attention. So you can consider this the era of the high point of NASCAR. The success enjoyed by the sport and by the teams really meant that budgets were not an issue. So the search for speed and the search for performance really turned into a technology's arms race. Teams had invested heavily in their hardware test solution, so the first efforts in simulation and the virtual assembly of the vehicle and the parts was to replicate that particular lab-based testing process. And then we would use those simulation models to then predict combinations not physically able to be tested on those specified test rigs. Efforts were centered around handling and ride performance at this point, and we're talking about damper selection and trying to control the vertical variation of the footprint of the tire. Early simulation methods were typically parametric based. Programs such as MATLAB, Simulink, AVL, and CarSim. Engineers used these methods to pretty great success in supporting their suspension designs and their setup optimizations. These early methods allowed the engineers to evaluate more designs and more setup changes in a much shorter amount of time without the need to build physical parts or cars and without the need to actually go to the racetrack. Engineers being engineers, they're always searching for a better, more accurate way to evaluate performance using these virtual methods. And we're always searching for better models and better methods to represent the performance of their race car at the racetrack. We then started to get into dynamic simulation methods, but then those could have been either parametric or multi-based physics. They were kind of the next step forward, both for handling and for ride performance. And we used tools such as CarSim, Atoms, and more recently, Dymola. These lab-based tests, while continuing to be used to support the engineering design process, were starting to be used now to help develop and validate the models that we were building. And these methods and these lab-based tests are still being used today to support our development and validation process. This was also the time where simulators were starting to get talked about, but they wouldn't really come into fruition until a little later on. That brings us to 2010, kind of to where we are today, and I call this the virtual era, virtual solution, where now we're using offline sims and DIL tool sets. So around 2010, simulators began to make their way into the conversation, and manufacturers looked at ways to bring this technology already being deployed in the OEM market space into motorsports. Probably worthy to note at this point that engineers had really become a part of the NASCAR process, and to the point where the OEMs were now asking and using motorsports to develop technologies that could be integrated now back into the production environment. The team environment within NASCAR provided much shorter time to market opportunities and didn't really have the inertia that a lot of the OEM processes had. Advanced tire models, driver models, DIL and HIL test rigs, applications of CFD technologies. These were all being developed within NASCAR or motorsports space and being then pushed back to the production environment. So now looking at this simple timeline, it's pretty clear that it took several decades for the engineering process to really mature in NASCAR. But as with all motorsports series, NASCAR has focused itself on now utilizing this virtual world environment to support the engineering process through a combination of offline simulation methods and the use of simulators. So now let's leave the NASCAR time continuum and start to talk a little bit about more of the details of the virtual world and the progression to rely on the simulators to support vehicle design and optimization. One of the biggest challenges we encounter in motorsports is the variables associated with on-track testing and how to extract good data through those changing conditions. These include variables such as environmental, whether it be ambient temperature, wind, unfortunately sometimes rain, physical variables such as track temperature, tire wear, tire give up, set-to-set variation, and sometimes control variables such as varying driver lines, throttle brake changes, and the subjective feedback that we then have to process and equate to engineering metrics. We go to the racetrack with the expectation of perfecting setups, body and suspension designs, and optimizing tire performance. But we are continuously fighting variables. And over the years, engineers have developed creative ways to manage these variables, but they're always present and oftentimes cloud our decisions and make data difficult to interpret. As we discussed, engineering tools, both simplified and advanced, were developed to provide engineers with the capabilities to understand their race cars, to support the design and race preparation at the shop, and to optimize the race cars when they're at the racetrack at a moment's notice. DOE and AI methods have been developed to help analyze an infinite number of options without ever having to build a physical part or have to go to the racetrack. Engineering groups have grown up from one individual performing basic record-keeping tasks to teams of engineers analyzing every aspect of their race car and developing relevant simulations, models, and methods to more accurately represent and understand their race car. OEMs have stepped up by providing engineering resources from everything from custom engineering tool development to at-track support. And many of them have often opened full-service technical centers. In addition, teams have created their own departments now responsible for advanced engineering methods and tools. Engineers who use these tools to prepare for the race weekend and to support all the on-track engineering responsibilities at the racetrack on the weekend. But in the end, with all these tools in place, we're still required to go to the racetrack to test, and we are continuously fighting the variables that cloud all of our results. In addition, there's also always been a gap between the metrics we derive from simulation methods and the subjective comments we receive from the drivers. Knowing what the driver keys off of, what they react to, how they want their car to feel, and how this translates to quantifiable metrics that engineers can use has always been our goal, and it's always been a struggle. No two drivers are alike, and therefore simulation and typical design processes struggle to equate these subjective comments to quantifiable engineering metrics. An example of this might be seen in the way that tire manufacturers oftentimes test or conduct tire tests for selecting a new construction, a new mold shape, or a new compound. Tires are built, a track is reserved for a number of days, teams from each manufacturer are invited to participate, and the test starts. Each team is typically given a series of tires to evaluate, and by the end of the test, the direction on acceptance is primarily driven by driver comments. And seldom, unfortunately, do these drivers agree with each other, and you're often left wondering what the correct direction is. And all this is complicated by weather, differences in car setups, track conditions, and teams who oftentimes want to be there to help optimize their own race car and not necessarily focus on the tire testing going on. Oftentimes when you're said and done, it's a guessing game as to what the right answer is. So there had to be another way to design, test, and quantify outside of the standard methods of lab testing, simulation analysis, and on-track testing. And this method should help engineers not only evaluate an infinite number of design and setup optimizations in a controlled environment, but also allow the driver to participate in the process and find ways to equate their subjective comments to some base engineering metrics. So the answer came by way of various forms of a simulator. This technology became the next big improvement in the tools that support the engineering process in motorsports. And man, what a valuable tool it has become. Simulators opened up a whole new world of possibilities in the search for optimum performance and provided an infinite possibility to understand and improve the vehicle. Benefits for using a virtual environment via a simulator would include reduced cost of on-track testing. Simulators provided a reduction in cost of not only track rentals, but cost of personnel, equipment, physical parts manufacturing, tires, fuel, travel, etc. They also provided a reduction in time to evaluate design and development options because the process did not have to wait for the availability of the racetrack. Simulators also had limitless development time. Sessions could be run on any day, regardless of weather or track availability. Sessions did not have to count against the team's availability of on-track budget, and more laps could be run without the worry of changes to the car, changes to tires, changes in track, environment, all those things. Simulator variants also offer the ability for both race engineers and drivers to evaluate designs and setups. The static simulator could be used to try out or evaluate physics and system updates prior to evaluating them in the dynamic simulator with a professional driver. Once updates are evaluated and approved, they could then be ported over to the DIL for driver evaluation. Next, the ability to control significant variables that would typically occur at the racetrack, and that might include weather, changing track conditions, issues with repeatability. All those things are now controlled within the simulator environment. Next, the ability for the engineer to evaluate new parts, new designs, and new setup theories without the need to manufacture or purchase any physical parts. The ability to include the driver's subjective feedback and have the driver be part of this virtual environment. This was probably the first time we were able to have driver comments be part of the engineering process, which significantly improved the results of the evaluation. And finally, the ability to evaluate new racetracks and give drivers experience and time behind the wheel at tracks that they might not have ever driven at before. And also with the changes in rules and the reduction in on-track testing, having the ability to conduct virtual testing is a significant benefit. Now, of course, there was roadblocks and hurdles that stood in the way of a successful implementation of the DIL in motorsports. Perhaps the biggest initial roadblock was drivers and owners' acceptance. There's several occasions that I witnessed where drivers and the owners pushed back pretty hard on use of the simulator, all while the manufacturers were excited about the possibilities. Many of the team owners and the drivers were concerned that it was just another glorified video game that could never be useful in the engineering process. Drivers were also concerned that they would not be able to truly drive the racetrack the way they would in real life, and that would lead to inaccuracy and poor findings. Early on, they might have actually been right because the physics models, the simulator capabilities, and this immersive environment were really only in their infancy and were not fully matured. Then there was the cost of the infrastructure required to house these full motion simulators. As previously noted, simulators come in an array of different possibilities, ranging from desktop versions to full motion platforms. And each one of them has a unique purpose and also comes with a unique and varying price tag. Then there was the engineering challenges, such as developing real-time accurate physics models to represent all the aspects of the race car, developing the virtual world, including the 3D track surface and environment required to immerse the driver in the virtual reality world, developing a motion platform and additional capabilities to allow the driver to feel the performance of the race car as they would on the racetrack, developing all the additional environment capabilities such as cockpits, braking systems with feedback, shifting and transmission, sound. All these inputs are required to ensure the driver feels like they are in the actual race car. And then developing the infrastructure to support the creation of the required inputs and the methods used to ensure that the inputs work properly in the simulator. And we're talking about details such as tires, aerodynamics, engines, steering systems, drivetrains. These all had to be at a higher level than those required for the offline simulation. And because drivers can take physics models outside the typical operating ranges of an offline simulation, the models must perform predictably and safely in these extremes. Over time, as the models and the environment matured, the owners, the engineers, and most importantly, the drivers became much more confident in the simulator, and its use became invaluable. The simulator became part of a three-pronged tool set in the arsenal of tools engineers would use and heavily rely on as part of their design and race preparation process. And that includes the offline simulation, where this software tool is used to evaluate and prepare options for the race weekend, and then at the racetrack to support at-track performance adjustments during the race weekend. Secondly, the simulator, as we talked about here, it's used to evaluate design and set of optimizations with the driver in the loop. And then finally, at-track testing. At-track testing will never go away, and it'll always be part of the development process. And it really does serve as a great and valuable confirmation and validation to all the work performed in the virtual world. Stackpole Engineering Service has been blessed and honored not only to enjoy a front row seat to the changes and advancements of the engineering process in motorsports, but also been blessed to be part of its growth. I'm still amazed at the changes that have taken place over the course of my career and humbled by the possibilities looking forward. As I look back at the 30+ years I've been involved in this field, I can't help but marvel at the accomplishments and the advancements that were made, the quality of the tools and methods that were developed, where we are today compared to where we even thought we would be back then, and where it looks like we're heading in the future. We started out on a quest for basic information about the tires and simple tool sets that were needed to help answer some questions that tire manufacturers and teams were asking. That has matured into a highly detail-oriented and comprehensive virtual environment where advanced testing, model physics, and simulation methods are the norm. But as always, engineers in motorsports are never satisfied with the status quo. We're always looking for the next big thing that'll give us a competitive advantage or a way to get another 100th of a second out of the race car. I'm confident this search, as we look forward, will include advanced tire models that account for thermal effects on inflation pressure change, physical changes to the tire, and overall grip capabilities, wear effects on grip, pressure change, and thermal performance, and material property changes and how they change over the course of an outing, and finally improvements in runtime speed. We're also looking at advanced tire testing methods to support a lot of these advanced models. Advanced vehicle model physics, whether it be for offline simulations or now for simulators. And finally, advancements in simulator technology itself, whether that be improved driver immersion, sound improvements, environmental modeling improvements, or improved driver control and feedback, whether that be improved braking systems, improved steering systems. In addition, Stackpole Engineering has been honored this year to support the Indy Autonomous Challenge, which is the world's first head-to-head, high-speed autonomous race at the Indianapolis Motor Speedway. The challenge is a collaboration between private, public, and academic institutions around the globe to challenge students to develop an autonomous Indy Lights race car and compete against each other at the famed racetrack. While this challenge is academic in nature, it does give a glimpse into potential changes in motorsports in the years to come. And I have to wonder if maybe motorsports might look like this in the future. Who knows? Wherever we wind up, I'm confident that engineers, engineering tools, simulation models, and the virtual world will play a key role. Over the course of my career, engineers in motorsports has gone from a swear word to an integral part of the success of any motorsports program. Thank you everyone for attending this session, and thank you to the Tire Society for allowing me to share my story. Also wanted to thank all my friends and family who have helped me prepare for this presentation. Every one of them has had a significant contribution to the advancement of engineering and the virtual world in motorsports, and I'm honored to be part of their story as well. Thank you again, and God bless.